All right, guys, in this video, I'm going to talk a little bit about drugs. And I want to begin with the biological basis of addiction. And I'm going to talk a little bit about uh, the neurons and how neurons are work normally. So I'm going to just sort of recap that. But then I'm going to talk a little bit about the rewards pathways and how drugs affect that. And so I want to remind you the cell that is in your brain is your neuron, and your neuron has dendrites, it has a nucleus and a cell body, um, it has an axon, and the axon is wrapped in myelin sheaths. The parts of the axon that are not wrapped in the myelin are called nodes of Ranvier. And then at the end of the axon, you have your axon terminals. And it is in the synapse where the axon terminals and the dendrites come together. They don't actually ever touch, but in that little space, that's where everything happens. Now, normally, when a neuron is triggered, it releases some chemical, some neurotransmitter. That neurotransmitter attaches itself to the receptors, and then the postsynaptic neuron will fire. Okay, that's normal. Now, uh, when this happens in what we call the rewards pathways, um, that is going to trigger usually dopamine, and that starts to get you addicted to whatever event triggered that rewards pathways. Sometimes it's just normal stuff. You played, a sport with your friend, you enjoyed it, that activated your rewards pathways, and in the future your brain will go, "Hey, we liked that last time. Let's do it again." And it'll create that sense of anticipation to do that behavior. Now, your rewards pathway is a few things, which includes your nucleus accumbens, but also includes different parts of your limbic system, your hippocampus, your amygdala, uh, different parts of your frontal lobe, and your anterior cingulate, which is part of your um, your frontal lobe, and then your prefrontal cortex there in the very front of your frontal lobe. So it's not just one thing. Your rewards pathways is a pathways. It's several parts of your limbic system and frontal lobe which sort of work together and are activated by dopamine. That's not important. I just want you to sort of have a visual representation of it. I'm not going to ask you which parts of the brain um, make up the rewards pathways, but some people like to see it. And the rewards pathways is going to be triggered by a lot of things. Getting that phone call from your crush, eating that uh, burger that's delicious, um, when you're trying to hunt that antelope that you and your family can eat, right? Both the anticipation of trying to kill that antelope and finally killing it and eating it, all of those things are going to activate your dopamine pathways or your rewards pathways. And what that does is that it creates a way for your brain to tell you, pay attention to this. This is important. You enjoy this, and we're going to do it again next time because this keeps you alive. Whether it's social or it's biological to literally eat, the rewards pathways helps you to focus on things that keep you alive. Um, so again, here you see the example of dopamine uh, clicking, first of all, being released and then binding to the receptors of the postsynaptic neuron. Now, what you're seeing here is the reuptake process. In a normal situation, chemicals are released by the presynaptic neuron to bind back to the dopamine or whatever other neurotransmitter. And then those chemicals bring the dopamine back into axon terminals. If any part of that process is interrupted, then that's going to affect the way your brain works normally. So, once again, here you see dopamine being released, binding to the receptors, chemicals being released for the reuptake process, and then the dopamine being um, returned to the axon terminals. Now, there are three types of drugs, what we call agonists, antagonists, and reuptake inhibitors. Your agonists mimic normal neurotransmitters. That is, they act like a neurotransmitter that you already have in your brain. For example, here you're seeing an endorphin being released by the presynaptic neuron. Uh, now, if this person takes some sort of opiate, well, the opiate doesn't actually look like the endorphin. This is just a representation. Obviously, your endorphins don't look like letter E's. Um, and if you take a dopamine uh, drug, it doesn't look like an O with a stick to it, but it's just a representation. What you see here is that the dopamine, or excuse me, the opiate doesn't actually look exactly like the endorphin, but it looks like the endorphins enough to fit into the receptor. And because it fits into the receptor, then that will trigger the postsynaptic neuron to fire. Um, okay. Now, antagonists do the opposite. So, for example, here you have ACH attaching itself to a receptor. But if you were to take, for example, an Advil, an NSAID, well, uh, what the NSAID does is that it looks enough like uh, the ACH in this scenario to cover, to fit into the receptor, but not trigger it. And so what you're seeing here is that the NSAID, like ibuprofen, for example, will just attach itself to the receptor, but not trigger the postsynaptic neuron to fire. That means that when other ACH get released, when they try to bind themselves to the receptors, they won't be able to, because the receptors will be covered by the NSAID or the ibuprofen in this scenario. And of course, that means that this postsynaptic neuron is not going to fire. Now, reuptake inhibitors interrupt the reuptake process. So here you have the example of dopamine attaching itself to the receptors. But now, when the body releases the reuptake chemicals, someone who takes a drug, like, for example, cocaine, the cocaine binds itself to the reuptake chemical, and that prevents the reuptake chemicals from taking the dopamine back to the uh, terminal axons. And so now these this dopamine will eventually click out of the receptors and then eventually click back in, and that will make that postsynaptic neuron fire again and again and again and again and again, because the reuptake process has been blocked by, in this scenario, the cocaine. Something like methamphetamines do something very similar, but not only do they block the reuptake process, but they also trigger more uh, dopamine to be released. And so not only have these guys uh, blocked the reuptake process, but also more dopamine gets released. And so now, not only will the dopamine that's there keep on binding to the receptors, but there's way more dopamine binding to all the receptors all around. Now, what you saw there, that examples or the examples that I've just given you, this has to do with the biological aspects of the drug. And that's quite important when we talk about pathological use. Pathological use meaning when people abuse the drug, um, because it is that process of uh, agonists and antagonists and the reuptake inhibitors that create tolerance. And tolerance is the amount of drug needed to produce the effects of the high uh, that the drug gives you. So the more drugs that you use, well, the higher the tolerance your body will build. Eventually, after you use a drug over and over and over again, your body is trying to stop that drug from affecting it negatively. And so it will sort of downgrade receptors. That means it'll take in receptors so that the so that the neuron isn't affected as much, or it might upgrade so that it takes twice as much to trigger it, or something along those lines. The body is actively trying to suppress the effects of the drug. There are other ways too. The body tries to metabolize the drug faster, get it out of the system faster, things like that. So the better your body gets at that, well, the harder it is for that drug to give you its high, to give you the effects. And so, in order to get the same effect that you got in the beginning, well, that means you have to take that drug more and more, higher and higher doses. Um, we all know somebody who can have half a beer and uh, they're already tipsy. And we all know someone that can drink essentially all night and never seem drunk. Um, that's because those two levels of tolerance are quite different for those two individuals. Another important aspect of pathological use is the withdrawal symptoms. So, because your body is trying to stop the effects of the drug, one of the things that it's doing is downgrading or upgrading the receptors, metabolizing the system, stopping the amount of, let's say, dopamine or serotonin that's being created in the body. It's trying to stop the effects. And so if you stop taking the drug, all of a sudden your body isn't sensitive to normal amounts of dopamine or to normal amounts of serotonin or whatever other neurotransmitter is being affected. And so that's going to have some symptoms. So every drug is going to be slightly different. But again, withdrawal is those physical and behavioral effects that occur when you stop using the drug. Now, substance abuse disorder includes tolerance and withdrawal. So that's as soon as we see someone who has a substance abuse disorder, we tend to see that their tolerance is very high and they are consistently taking the drug to prevent the withdrawal symptoms. Um, but often that's not the only aspect of pathological use or substance abuse disorder. Usually, these individuals feel like they've lost the ability to control their drug use in important situations, social situations, at work. The doctors tell them you're killing yourself, and they still cannot control it. And of course, their risky behavior increases. Uh, Taking the drug by itself could be a risky behavior because it affects your health. But also, we tend to see that these individuals have, risky sex patterns. They have sex with strangers without protection. They might drive while under the influence. They might get themselves in trouble with the law. It's important to understand, though, that pathological use isn't just about the physiological aspects. The physiological aspects are important, but lots of people drink, and not everybody who drinks has a substance abuse problem. Not everybody who drinks is an alcoholic. There are other aspects that affect that, both psychological and sociocultural factors. Now, I do want to separate the different types of drugs: depressants, opiates, stimulants, and hallucinogens. Okay. Depressants slow down neural activity. That means your brain slows down. It's not as active as it is if you are not drinking. Um, Depressants usually affect GABA receptors, and I'm going to focus a lot on alcohol when I talk about the specific ones, but also barbiturates and benzodiazepines are also depressants. Opiates, on the other hand, as I already mentioned, mimic endorphins. That means that they inhibit pain and they increase feelings of euphoria, feelings of gladness and happiness and sort of wonder. People often feel quite uh, beautifully when they are in under the effects of opiates, and that's usually the reason why they take them, because they want to feel happy and glad, and opiates often do that. This is going to include drugs like codeine, heroin, oxycodone, hydrocodone, methadone, morphine, and opium. And I'll talk about a few of those as well. Um, Stimulants, on the other hand, are the opposite of depressants. They're speeds, and stimulants increase neural activity. That means that your brain is now working faster than normal. And this is going to include caffeine, which I'll talk about, nicotine, cocaine, amphetamines, and methamphetamines. And also things like ecstasy, MDMA, are stimulants. Whereas hallucinogens distort perception. That is, you hear, smell, taste, touch, sense things that are not actually happening. And that's going to include sort of milder hallucinogens like marijuana, and then uh, uh, more severe hallucinogens like LSD and others.